Good morning, students. We'll learn about cache memory in this class. Cache memory is the fastest component in the memory hierarchy. Among all the memories, auxiliary memory, main memory, cache memory is the fastest memory. And when we execute a program, there may be some looping statements. Okay, so that need to be repeated so many times. Or there may be subroutines. Okay, when a subroutine call is given from the main program, the sub function or a procedure, the subprogram may need to be repeated. The subprogram may need to be called again and again, right? Many times. So we refer these programs, okay, these part of the program, the repeated part of the program, such as loops, okay, the statements that come under the loop or the statements that come in the subprogram. Okay, we refer this as active portion of the program. So if these active, every time when these statements, these instructions need to be repeated, the CPU refers to main memory. And we know that the most time-taking process in the computer processes the memory access. Okay, that includes memory access means locating the data or the instruction in the main memory and then getting it into that, transferring that data or instruction into the CPU register, into one of the CPU registers. Okay, so that is access. So it is a most time-taking process. Okay, the speed of the CPU and the main memory does not match. So if these active portions, such as looping and the repeated part of the program and the data, if these active portions are placed in a fast memory, this reduces the access time. Correct? The average memory access time can be reduced, thus reducing the total execution time of the program. Okay, always the aim of the computer process would be to reduce the execution time of the program. So such a fast small memory, okay, is referred to as cache memory. So whatever the active portion of the program, the CPU need to execute repeatedly, that is stored in the fast memory, okay, called as cache memory. Here, this shows how the CPU communicates with this cache memory and main memory. And here main memory has 32K words. Each word has 12 bits. So the size of this main memory shown here is 32K by 12. Okay, 32K words means 32 is 2 power 5 is 32 and K refers, this means it is 1024. Okay, 1024 words. That is 2 power 10. Okay, 2 power 5 into 2 power 10 is 2 power 15. So the number of bits used to refer to this memory. Okay, number of bits in the address line, that is to refer to this each word in this memory that has 32K words is 15. Okay, 15 bits. 2 power 15 is 32K. And each word has 12 bits. This is the size of the main memory shown here. And cache memory, it is the size of this cache memory shown here is 512 words. It is a small memory. Okay, comparatively compared to main memory, it's a very small memory, but can be accessed faster. The size of this is 512 words and each word having 12 bits. Okay, the size of this cache memory is 512 words. Okay, each word having 12 bits. And the basic operation of the CPU is like when the CPU need to refer to a particular word in memory. Okay, it first refers to the word, it looks into this cache memory. Okay, the CPU first examines in the cache memory. If that word, okay, that the CPU want to execute is available, it may be an instruction or it may be the data. So if that word is available in the cache memory, it accesses that word. CPU accesses it faster from this cache memory. If it is not available, the CPU looks for that particular word in main memory. Okay, CPU examines this main memory and it transfers the word from main memory into the CPU. Okay, it takes a lot of time to transfer word from main memory. Okay, so the more the data is available in the cache memory, it is faster. The execution would be faster. Okay, that is the reason the active portion of the programs are transferred to cache memory to make the process of the CPU faster. It can access it faster, and so the execution time will be reduced. Execution can be done faster. So initially CPU examines the cache memory for any word, okay, to search for any word. If it is available, it accesses this. Okay, if it is not available in cache memory, then it looks into main memory. Okay, then it transfers. So what is a hit here? When the CPU examines this cache memory for a word, and if that word is available, okay, we call that condition a hit. Okay, when the CPU searches for a word in cache memory, and if the word is available, okay, at that time in cache memory, it is called a hit. And when a CPU search for a word in cache memory and it is not available in cache, it is called, okay, we refer that as miss. Okay, because the word that the CPU is looking for, execution is not available. So that is called a miss. And when there is a miss, means the data or the instruction is not available in cache memory, it has to be brought from main memory to cache memory. Okay. So here the other condition may be when it has to be the word that is not available in cache memory may need to be brought to cache memory, and the cache memory may be full. Okay, if it is full, some already existing word need to be replaced by the new word that is that is moved from main memory. So which word can be replaced? Okay, for that we have replacement algorithms. Replacement algorithms are used to replace the existing word in cache with the new word that is coming from main memory. So that way, when the word is not available in cache, it has to be brought from main memory. And if the cache is full, the word that is available in the cache memory is replaced by the new word. And the performance of this cache memory is measured, okay, with the hit ratio. Okay, what is hit ratio? It is the number of hits. Hit ratio is measured by calculating this number of hits by the total CPU references to memory. The number of times the CPU refers to this particular memory for a word. Okay, and if it is available in the cache memory, it is hit. If it is not available, it has to be taken from main memory. The number of hits by the total number of times the cache memory is referred by the CPU. Okay, that is hit ratio. Okay, so what we understand from this, the more active, if the repeated words are available in cache memory, the hit ratio will be improved. Okay, so the performance increases. Whenever the CPU search for a word, it is available in cache memory. CPU can access it faster. The transformation of data from main memory to cache memory is referred to as the mapping process. Here there are three types of mapping. One is associative mapping, direct mapping, and set associative mapping. Associative mapping. Associative mapping is, here this cache organization uses associative memory. We know what is associative memory. It is a content addressable memory. Here the search is done using the content, not by the address. Okay, so here how this mapping is done. The associative memory stores, here we are talking about cache memory. Okay, so it is cache associative memory. Cache associative memory, the cache memory that is searched by the content. Okay, that is searched by the content available. So here the cache associative memory, it stores both the address and the content of the memory word. Okay, here the address, this is the main memory location where this particular word 3450 is stored. Okay, this is the address in the main memory where this word is stored. And the same way here we have the address. Okay, each word in the cache memory consists of the address and the data. Yes, we have seen that it is a 15-bit address, right? Here main memory is defined as a 32K word memory. So the number of address bits needed are 15 bits. Okay, 15 address bits and 12 bits for the data. So here, this is the octal representation of the address. Each digit in this octal refers to 3 binary bits, equivalent to 3 binary bits. As we have 15 bits in the address line, so here we have 5 octal digits, each representing 3 binary bits. And the data bits in main memory are totally 12, right? 12 bits of data. So we use this 4 octal digits to represent those 12 bits, each having 3 bits. Okay, so here in the cache associative memory, we have the address part and the data part. It contains both the address and the data, corresponding data. Okay, so when the CPU want to refer to a particular data in the cache memory, in this cache associative memory, it places that address in the argument register. Okay, the address is placed in the argument register. And that address is compared with the address that is stored in the cache associative memory. Okay, so when this address matches with the address that is placed by the CPU in the argument register, it is the corresponding data is accessed. The CPU accesses the corresponding data for execution. Here, even though we are using the address, it is the content. Okay, it is a part of the content of the cache memory. Okay, so this type of mapping the data, okay, between main memory and the cache memory is this way of mapping is called associative mapping. It stores both the cache associative mapping. Okay, this cache associative memory stores both the address and the data in the memory. And when the CPU want to refer to a data, it places the address in the argument register, and that address is compared directly with the address in the cache memory. If it is available, the data is accessed. If suppose the address that is placed by the CPU is not available in the cache, it has to look for this into the main memory. Okay, it accesses the data from the main memory. The data is not available in cache. There is a miss, so it has to be accessed from main memory. Here in the available space, the next data element will be stored with the address and the corresponding data. And if suppose the cache is full, if the cache memory is full, the existing data need to be replaced by the data that is brought from main memory. So there one of the replacement algorithm. Okay, we will discuss about it later. One of the replacement algorithm is used, okay, using which the existing data is replaced by the new data, which is no longer needed. Okay, already existing in cache, but it is no longer needed. Okay, such data is selected and replaced with the new data. So it can be easily accessed by the CPU. And the second type of mapping is direct mapping. This associative mapping is expensive, okay, in a way that here there are 15 bits, right? So this entire address that is placed by the CPU need to be compared with each bit in the address part of this cache memory. Okay, and every bit will have the match logic, okay, as we discussed yesterday, the match logic to compare each bit with the content that is to be searched. Okay, so maintaining that, it is expensive. Okay, this method is a little different from that. The address, okay, here this is the main memory having 32K words and each word having 12 bits. So the address bits required are 15 bits, data is 12 bits. Same here, we have the cache memory, 512 words and each word having 12 bits. So the address needed is 2 power 9 is 512. So 9 bits are needed to specify the address of these 512 words, and data bits needed are 12. And this is the main memory address 00000, the 15 bits, correct? And it is represented in octal here. So we have 5 digits, 5 octal digits. So the main memory locations here from 00 to, okay, 757s. This is the octal representation of the 15 binary bits. And in this direct mapping, okay, the 15 bits of this address are divided into 2 fields. One is the index field and the second one is the tag field. Okay, the most significant 6 bits are used as a tag field and the least significant 9 bits are used as index field. This index field is used as a address to address, okay, to refer to the words in cache memory. Here the cache memory is addressed by the least 9 bits. Here we know that the address bits required to refer to the words in cache are 9 bits. Okay, that is the reason the least significant 9 bits are taken as index. And this index is used to address the words in the CPU. Okay, 000 is the first address of the first word in the cache memory. Okay, 000 is the first word, address of the first word in cache. Okay, that way. The octal 9 binary bits are represented as 3 octal bits here. And the data part in this cache memory includes, okay, the actual data and the corresponding tag. I said that here the most significant bits, most significant 6 bits are used as tag. Okay, that is to identify the data. Okay, corresponding data. We use these 6 bits as a tag bit. Yeah, you will understand it here. The address of this main memory, 5 octal digits. It's wrong here, 6. So this is the first location in main memory, 5 zeros. And this address is divided in direct mapping. This address is divided into 2 fields. The least significant 9 bits, okay, that is 3 octal digits 000 is used as index field to refer to the as an address for each word in the cache. And the most significant 6 bits, okay, the 2 octal digits are used as a tag that is associated with the corresponding data. Here the data is 1220. Okay, so the data is 1220 and the tag that is associated with this, this one, that is actually the most significant 6 bits of the address, main memory address. Okay, so this way the organization, cache organization is different, okay, in direct mapping. And here if you see this 777, okay, that is this data, okay, it is stored this way. The data is this and the tag is the most significant octal 2 bits, 2 digits, 02. And this these least significant digits 777 are used as the address. When the CPU places the address in the argument register, when the CPU places, example it is if the address placed is 00000, okay, and it is divided into 2 parts. This is considered as the index value, and this is used to access the particular location in cache, and this is compared. Okay, this is the tag field is compared with the tag in the cache memory word. Okay, if this matches with the search word, here it is 00 and the address that is placed by the CPU also has 00 in the tag. Okay, so if this matches, if the tag matches with this, the corresponding data is retrieved. If it doesn't match, then the CPU has to transfer data from main memory. But here the problem is, let's take this. If the CPU want to access this data 6710, it places the address 0 to 777, and this is considered as an index to access the data from cache. So this particular location is selected, And 02 is considered as the tag field, and it is compared with the tag in the cache memory in the corresponding word. When it is compared, it matches. Okay, there is a match. So data is accessed for processing. If suppose this is the address, okay, this is the data CPU want to search 4560 that is stored in main memory 01777. And when it places this in the argument register 01777, this is taken when it CPU searches in the cache, the address 777 is available. Okay, and the word in that address is checked. And the tag field here is 01. When it is checked with this, there is no match. Okay, it is not matching. So this data will not be accessed. Okay, so CPU now has to access the data, that corresponding data 4560 from the main memory. Here 6710 has 777 as the index address, and even this 4560 has the same index address, and this 2340, okay, if this you take, this also has the same index address. So this way, when the data that has the same index address but have different tags, okay, it is difficult to search those data. Okay, when the index address is the same for many data elements and the tags are different, then in this case it is difficult to locate the data. It takes a lot of time because the address is found. Okay, if initially the address itself is not there, directly it can search from the main memory. Okay, so the hit ratio will drop here. Okay, the performance will decrease. So to overcome that problem, we have set associative mapping. In this set associative mapping, each word of cache store 2 or more words of memory under the same index address. Okay, in the same index address, each word stores 2 or more data. Okay, and the corresponding tags. If the main memory has 00001, okay, so this in this location the main memory has 3450, and at this location 02000 the data in main memory is 5670. The earlier case we have discussed that when the address index address is same and the tags are different, then the data cannot be found, right? In this case, the cache stores more than one data. Okay, it may be 2 or more data. That depends on the size of the cache. Okay, it may also store more number of data elements with the same index address. Okay, so here 000 and 01, the first data element, and with the different tag, but with the same index address, 02, the next data element is stored. Okay, if suppose the data to be searched as 5670, first, it locates the position in the cache. So 000, it checks for this index, it is found. And then it checks the tag 01. Okay, it compares this tag with the tag in the address that CPU placed. Okay, here it will not match with that because the tag is 02 there. Okay, so then if there is no match here, this will be compared. Okay, in the same word we have the other tag element with the corresponding data. So this will be compared, and here is a hit. Okay, so the data is found. So here the number of bits in each word, the word length is increased, correct? Each word has 12 bits in cache and 6 bits are added as a tag field here. Okay, so this is the data, 12 elements. In octal we have 4 digits. Each digit represents 3 bits. So that 12 bits plus 6 bits for tag, 6 plus 12, and we have 2 words. Okay, in this cache organization there are 2 words stored with the same index address. Okay, so here this way 6 plus 12 of 2 words. Okay, so the word length is 2 into 6 plus 12, it is 36. So what is the total memory size? Okay, we have seen that the cache memory shown has 512 words, and each word having 12 bits in the earlier case, but in this set associative mapping, we have 36 bits for each word. So it is the total memory size is 512 by 36. The size of the cache is increased so that it will have place for storing more data elements that comes with the same index address. So the search will be easier. With one address, the CPU can locate more than one data. Then we have these things in cache. Cache initialization. How is cache initialized? When it is initialized, when the power is applied to the computer, cache is initialized, but there will be no data in the cache. Okay, so all the bits need to be set to 0. And the other time when cache is initialized is when main memory is loaded with a complete set of programs from auxiliary memory. When the CPU want to execute a new program, it loads that program, okay, a new program into main memory from auxiliary memory. Okay, so that case, cache is initialized. Means initializing means setting the words in cache to 0. That is done by using the valid bit. Initially, when there is no valid data in cache, the valid bit need to be set to 0. All the valid bits are set to 0. So that initializes the cache, means there is no valid data. And when the CPU start executing the program, okay, this new program that is loaded into main memory, the active portion of the programs are identified and are brought to cache memory. And the corresponding valid bits are set to 1. Okay, so valid bit indicates whether or not the word contains valid data. When a new program when a new program is loaded into main memory, okay, when the CPU start executing that program, this active portion of the program need to be brought to cache memory, right, for easy access. And once the data active portion of the program that is being executed is loaded into the cache memory, the valid bits are set to 1. Okay, so when the valid bit is 1, means there is active instructions in the program in the cache memory that can be used for the current execution by the CPU. And writing into the cache. How the reading from the cache is done. When the CPU finds a word in cache during read operation, it is directly accessed from the cache. Okay, main memory will not involve in that. If suppose the CPU want to access data from cache memory, right? Initially, when the CPU want to access some instruction or data, it looks into cache memory. If it is available, it is transferred to CPU directly. Okay, main memory is not involved in this operation. If it is not available, if the instruction is not available, then CPU has to look into this main memory and accessed. So reading is simple. And for writing, okay, when a data is written, when CPU want to write data, okay, the data is read from the cache, accessed from the cache, and through the program, some changes are made, and if it has to be written back. Okay, so that case, the data in the cache is updated. Okay, when the CPU update the data in the cache, the corresponding same data will be available in main memory, correct? Okay, so to make sure that if you want the same data, okay, the updated data in main memory, it has to be updated when the data is updated in cache. Okay, so there are two ways of doing it. First one is write through. Write through is main memory is updated in parallel with every write operation done in the cache. So whenever there is a write operation performed in cache, the corresponding data in main memory is also located and updated. So main memory will always have the same data as it is available in the cache. Okay, that would be helpful when main memory is directly accessed by the IO devices. Okay, without having the involvement of CPU, like through DMA controllers. If there is a direct access, if it is when the cache is updated, the main memory, if the data in the main memory is not updated, the IO device will not get the valid data, okay, the current data. It will access the old data that may be invalid because it is already changed here. Okay, so immediately changing, whenever a write operation is performed in cache, updating it in main memory, immediately updating it in main memory is write through. Okay, this method of writing is write through. So here the benefit is it ensures that the data residing in main memory are valid at all times. Whenever it is changed, it is updated. And the other method is write back. Okay, write back is only the cache is updated during the write operation. Whenever a write operation is performed, main memory is immediately not updated, but the location in cache where the data is updated is marked by a flag. Okay, it is marked by a flag. And later, when the word is removed from the cache, it is copied into main memory. Okay, instead of updating the main memory, the corresponding word in the main memory immediately, here when the write operation is performed in cache, a flag is maintained. Okay, so the flag is set. It is to mark that, it is to remember that there is an update that need to be done in main memory. Okay, corresponding word in main memory. But as long as this data is available in cache, main memory will not be updated. And when it is removed, when the data need to be removed from cache memory, it updates the data in main memory, and the cache data from cache memory is removed. Okay, so the updated data will be either available in cache or in main memory in this case. This method is write back. That's about cache memory. Cache memory is the fastest memory in the main memory hierarchy. In computers, cache memory is maintained to speed up the process of CPU. Okay, the speed of the CPU is different from the speed of main memory. CPU is faster than main memory. So if there is a faster accessing memory available, it would be easy. It will reduce the execution time of instructions. Okay, so for that, this cache memory is maintained. And during the execution of program, the active portion of the program are identified and are brought to cache memory. Okay, so that those repeated part of the program, instead of accessing main memory for every instruction, okay, those are repeated again and again in main memory. So those instructions are brought to cache memory, okay, to make the access faster. And here a 32K word by 12-bit main memory is shown. Okay, it has totally 15. Then address bits needed to represent this 32K words are 15 bits. Okay, and each word has 12 bits. Cache memory has 512 words and each word has 12 bits. So the operation is CPU first look into cache memory for any word, okay, for processing. If it is available, it will access. The access is faster. If it is not available, only if the word that the CPU is looking for is not available in cache, it looks into main memory. Okay, it accesses that from main memory. So this we call a hit. When it is when the CPU search for a word in cache memory, if it is available, it is called hit. And if it is not available, it is a miss and it has to get it from main memory. And the performance of the cache memory is measured in terms of quantity called hit ratio. Hit ratio is the number of hits by then, so total CPU references to memory. That is the number of hits plus misses. And mapping is the transformation of data from main memory to cache. The three types of mapping are associative mapping, direct mapping, and set associative mapping. Associative mapping is the cache organization uses the associative memory, and okay, each memory word stores the address bits and the data bits. When the CPU wants to search for a particular data, it places the address in the argument register, and that address is compared with the address bits in the cache memory, okay, cache associative memory. When the address matches, the corresponding data is accessed. Okay, so this way using address, but here address is the part of address is the content here. Okay, address is stored as a content of cache. Okay, so this type of mapping, the main memory to cache memory, is called associative mapping. And the second type of mapping is direct mapping. In this mapping, the main memory address of 5 octal digits is divided into two fields. One is index field, that is used as the address to cache memory. And the other part is, the second field is tag field. The 6 bits are used as tag field. 6 bits means here in octal 2 digits are used as tag, and the octal 3 digits, least significant 3 digits, are used as index. Okay, index is to refer to the words in cache memory, and tag is added as the part of the word. The data field is associated with the tag. The data with the tag field, okay, as a content of cache memory, and this is the address. The least significant 3 digits of the main memory address is used as the index address. First, the address is located. Okay, the word is located using the index address, and the tag is compared with the given tag. If that matches, the data is accessed. If it is not available, it is brought from main memory. If data with more tags are available in the with the same index address, okay, it is difficult to locate them in this organization. So we have set associative mapping. Here, 2 or more words, data words with the corresponding tags form a set. Okay, so here this form a set with the same index address, but 2 different data elements with 2 tags, different tags. One is 01 and the other one is 02. Okay, so this is set associative mapping. With the same index, more than one data element can be accessed. And in this chapter, we also have virtual memory. Okay, we have one more topic, virtual memory, that we will finish tomorrow, and we will move on to the next chapter. Any doubts here? No doubts. Okay.